Vanakkam, Namaste, Namaskar, all of you. Welcome back to Jal Prayag. I'm going to continue from the definitions where I had stopped earlier. If you remember, I had done part one of definitions. So let us start off with the remaining part of definitions. I might go into a part three also. So let us finish this topic today, and we'll see whatever is left. I can go as part three of definitions. As a quick recap of what we have finished last time, you can see we did light displacement, we did load, dead weight, present, dead weight aboard, available, and the last one was your water plane coefficient. So these were the definitions, 7 definitions which we finished. Let us continue with a few of them today, and whatever remaining I'll go as part 3. Let me start off with the 8th definition, which is called block coefficient. Now, if you want to just compare what we did in water plane coefficient, the word coefficient, we have realized that it is a kind of a multiplication factor. So whenever I want to use a word coefficient, I'm trying to give you a small multiplication factor. That multiplication factor is going to help me to find something else which is not very easily calculable. So if I cannot calculate something very easily as a common day-to-day life, I give you something called coefficient. So your water plane coefficient was a coefficient where I was using a 2-dimensional calculation. Now, next extension, the next step extension is your block coefficient. Block coefficient is a 3-dimensional calculation. So let us just quickly go on that. We are all aware that ships do not generally come in box shape or rectangular shapes. But usually when we are talking about basics, it's very easy to understand the concept using the box and the rectangular shapes. So that is why I use it. But in real life, it's very rare that you will get something in a box and a rectangular shape. Now, most of the stability calculations, if you agree with me, one of the important part of calculation is calculation of displacement. Now, we saw earlier itself displacement, how you can calculate using your flotation principle, where one of the important part of the displacement calculation was underwater volume. So again, for me here also, I need an easy method to calculate the underwater volume at any particular draft. So normally what we do is, for using this concept of block coefficient, let us assume that I'm going to cut a vessel exactly at the draft level horizontally. So I'm going to show you a picture. So this is a vessel. I'm going to cut this vessel exactly at the draft. I did the same cutting in water plane coefficient also, but all I wanted was water plane area. But now I'm interested in the 3rd dimension also, which is the draft. So that means, let us say this is the water line, and whatever is below is called your underwater volume. You can see that this underwater volume is going to change with drafts, and that is very evident in all your hydrostatic tables also. And at the same time, I've just given you 3 levels of watermarks just to show you that the underwater volume is going to change with drafts. Ship shapes are not constant. They are sometimes not symmetrical. They keep varying with your drafts also, as and when we keep increasing your drafts. So for me to calculate the underwater volume of a real ship shape is not very easy. Okay. So I'm just giving you 2 possibilities of shapes of underwater volume, where you can see the underwater volume shape is not constant. At the same time, it changes with your drafts. Now again, I have a simple methods of calculating the underwater volume at that particular draft, and that is where this concept of block coefficient comes into picture. Let us look at it. Something very similar to water plane coefficient. If you remember, there also I gave you a concept of extremes that was two-dimensional. So I was talking about concept of extreme length and breadth. But now I'm going to go to the third dimension, which is your draft. So if you look at this small picture, I can see I've cut the vessel exactly at the draft marks, and I'm interested what is below, that is the underwater volume. You can see I can very easily show you what is this extreme length here, extreme breadth here, and the maximum, what is the depth, which is the draft for your calculation. Can you imagine, just in a very simple way, let us say this yellow color shaped picture which is shown to you is a small souvenir you bought from a shop, and you are asking the shopkeeper to pack this for you so that it does not get damaged. So I'm sure he's going to pick up an empty box. The empty box is going to be a rectangular shape. And let us say, coincidentally, this empty box exactly matches with extremes of your boat shape. And that is how normally packaging also comes. So if you go and look at the original box of any souvenir, it'll come exactly at the maximum levels. Now you should realize this small souvenir boat, you will put it in the box and you will realize that there will be a lot of empty spaces. So you can see it in this picture also. The yellow color boat is matching with the extreme dimensions of your packing box, but you still have a lot of empty spaces. So for me, calculation of extreme length, breadth, and the draft is very easy. Now, what do I do? If someone tells me that your boat is occupying a space which is a percentage of this extreme length, breadth into draft, and I've given you a small example as 70%. Let us say this yellow color boat is occupying 70% of that packaging box. So very easily I can calculate the underwater volume or the volume of that particular boat. So this is what is the answer. The boat's underwater volume, which is the yellow color shape, is the extreme multiplied by a coefficient or a percentage called 70%. This percentage, what you were given for calculation, is called Bloch coefficient. So it's very similar to water plane coefficient. It is called Bloch coefficient. I've given you one more picture. The same formula I'm going to write again. Boat underwater volume is equal to L into B into D into Bloch coefficient. So this Bloch coefficient is 70%. I can rephrase this equation. So what is CB? This is what is CB. Underwater volume of that particular ship or a boat divided by the extreme dimensions. So this is a very easy way of calculating underwater volume. And once you get underwater volume, we all know that I can proceed with that figure what of underwater volume what I got, I can use it for my displacement calculation. So that is the advantage of Bloch coefficient. You will come across a lot of questions in basic stability also, and most probably you will get it in the advanced also. Let me go to the next definition, which is called tons per centimeter. Now, tons per centimeter is one data which is given to you in hydrostatic particulars. You will see is very, very useful or very handy, is a kind of a quick reference guide for a mate, chief mate, or anyone who is doing the cargo watch. Let me give you a small example before I start. This definition is slightly bigger. I'm going to take a couple of slides because it's a very important feature also. Let us say you are on a container ship and you are doing a watch, and somebody is going to load a container. I'll take an example of loading. Let us say that container weighs around 20 tons, for example. Now, if you load that container of 20 tons, if I get a small mental figure on back of my mind telling that, okay, if I load this 20 tons of container, what is going to be the change in draft for me? And that is what is the concept of tons per centimeter. Okay. So you can say that same change in draft can come if you discharge a 20-ton container also. So that is what is the benefit of this tons per centimeter. Gives a very quick guide for the mate, so he can very easily guess that what is going to be the sinkage or risage of the vessel's draft. Okay, so TPC is the number of tons required to sink or rise a ship by just 1 centimeter. So 1 centimeter draft change will be observed. In other words, what weight should you load to increase the draft by 1 centimeters, or what weight you should discharge to reduce the draft by 1 centimeter. So this is what is your tons per centimeter. Now you should realize that I can translate this into a slightly different definition, which we have already done. You should agree that when I say the draft has changed by 1 centimeter, so obviously there has been a small change in the underwater volume also. And the change in underwater volume has happened with a depth of 1 centimeters. That is what you should agree. Okay, I've just shown you a small picture here. You can see on the top picture, he has cut the boat exactly at the waterline. And obviously you will have a water plane area. And this water plane area, if I change it by 1 centimeter, that means there's a small change of depth at that water plane area by 1 centimeter. So this is what I'm interested in. This is what will give me the definition of tons per centimeter and a calculation formula as well. So once I know what is this change in underwater volume just because I shifted by 1 centimeter the draft, I can calculate how much did I change the displacement also. Because with the change of underwater volume of 1 centimeters, I will get a change in displacement also. And this change is because of 1 centimeter. Hence, that is why it is called the change in displacement is also called in TPC as far as your risage and sinkage is just 1 centimeter. You will see in US vessels and all Western countries, the same TPC is also called differently as tons per inch. It is called TPI. Concept is same, only thing is there he's asking rise and sink of 1 inch. But let us go by centimeter, is much easier and we are used to this unit. Okay. Now I'm going to show you the same TPC experiment by our old flotation experiment. We have already seen a couple of examples of flotation experiment. I'm giving you the big container, then an overflow pipe and an overflow container also. Let me take a weight of 100 tons or a vessel of 100 tons. I'll lower it. I let it float freely. That means I'm not holding it with any crane. I'm just allowing it to float. You can see it is partially immersed. And going by the flotation principle, right now that object is feeling weightless. So loss of weight is 100 tons. So obviously this overflow container also will have a water which is overflowed equal to 100 tons. So that was our old flotation principle. Now let me add 20 tons on this vessel. So I'm going to add 20 tons. So very evidently, it's going to sink more. There's going to be more displacement. And for example, I'm just taking, let us say this sinkage was exactly 1 centimeter. So it was just 1 centimeter sinkage. So if I have this 1 centimeter sinkage, you all should realize that that means there's a change of displacement from 100 to 120. So I'll get that same extra water here also. Now this water in the overflow container will weigh 120 tons. So based on this principle, you can just guess one thing. If my draft changed by 1 centimeters, how much did I add to get that 1 centimeter change in draft? And that is what is called TPC. So right now for me, TPC is 20 tons. I'm going to derive a formula very simply using the displacement concept, which I've shown you here. Let us quickly see that. You should agree the extra underwater volume caused was because of 1 centimeter sinkage. So that extra which you overflowed can be calculated as the length into breadth of this particular vessel or object Okay, that is the water plane area for that vessel, because I've shown you rectangle is very easy, length into breadth. And the extra depth what you got was exactly 1 centimeter. So this is that extra volume. So do you agree L into B into that 1 centimeter is the volume, extra sinkage volume. And if I go by my displacement principle, I can multiply the seawater. Let us say I was floating in the seawater. And let us say that this answer what I got was 20 tons. So for me, right now, TPC is 20 tons. I can write it in a slightly different way. Your L into B at that particular draft is also called as water plane area at that draft. And I've converted 1 centimeter into meter, that is 1/100. And remaining everything is same. So you see here, I have a small constant. The constant mean at that particular draft, water plane area is not going to change. So that is why I've written A, which is water plane area, divided by 100, because 1 centimeter I've converted into meters. So this formula in brackets, what you see is actually volume, or is a change in volume. That is what is the change in volume, extra volume, multiplied by the density of the water in which you are floating will give you the TPC. So I'm going to use this formula in all my calculations, A by 100 into density. How I got it? I got it by a simple displacement formula, where I'm seeing that what was the change in the underwater volume, so what was the change in displacement. So why did you sink or rise by 1 centimeter? It was because I added some weight, and that is this weight actually. So you can calculate it by using the displacement principle. Okay, I'm going to show you again the same formula, but I'm just going to go further. So let us say at any draft of the vessel, I know the water plane area. So I can use the displacement formula to find the change in weight, because the draft sinkage or risage is exactly 1 centimeter, which is 1/100. So this is what I've written. What is the change in underwater volume at that time when I put that extra weight? It is A by 100 meter cubes. Now, when I know the change in underwater volume, I have written A by 100 is the change in underwater volume multiplied by density is called change in displacement. So this is what is your TPC. The change in displacement because you rise or sink by 1 centimeter is called your TPC. Okay, it is written as tons per centimeter, or T dot cm to the power of -1. Both are same, it's exactly the same. Now you need to realize this formula has got two features. One is the water plane area, and other one is your density of the water in which you are floating. So you should come to a conclusion that TPC is directly proportional to A. TPC is directly proportional to the D also. So let us quickly split this and see how it is going to change when something else changes. So the first one is TPC directly proportional to the water plane area. Let us say I'm floating in seawater or freshwater, doesn't matter. I'm floating in some water. As and when my water plane area changes, my TPC also will change. So for a ship shape, the water plane area keeps changing with the draft, and hence TPC also will change with your draft. And this is very evident in hydrostatic particulars. You can go and have a look. So this is the first change. I'm in a particular water. I keep changing my draft. Obviously, the TPC also will change. It cannot be constant. Now the second, let us say what is the second? Second one is density. Now, how to understand this? Let us say that I am at a 5-meter draft in salt water. But the same ship can be at 5 meters drafts in freshwater also, or in dock water also. You should realize TPC is proportional to the density. That means how much tons you need to sink by 1 centimeter in salt water cannot be the same for how much tons you need to sink in freshwater. You are at the same drafts, doesn't matter. So ship floating in different densities, TPC also changes with the density of the water. So this is something important. Why? Because you have to convert this when you are solving problems if you are not in a particular water, which is your salt water. So we can calculate this TPC of any water with the same displacement formula I've just shown you. Let us say TPC salt water at any draft which is given to you in your hydrostatic tables, which is made only for salt water. I'm just taking a small example. Let us say it was written as 25 tons per centimeter. I can still use this formula also, A by 100 into 1.025. Why? Because I'm floating in salt water, is 25 tons per centimeter. Please note, if any question, he does not mention the TPC salt water or dock water, fresh water. Please assume it as salt water and carry on with the question, because that is what it means. If it doesn't mention, it is salt water. Now, let us see how I can change or calculate this value when I'm floating in some other water. Let us say the previous example, which I gave you, 25 tons. For a example case, let us say I was at a 5-meter draft. Okay, I was at 5-meter draft and my TPC was 25 tons per centimeter. Now, let us assume that I'm going to be at the same 5-meter draft in a dock water density of 1.010. So how can I calculate? I'm still going to use the same formula only. He already gave me what is in salt water. So I know what is it in salt water. So if I put that in salt water, you will see that left-hand side of this equation will have 25. Then I will have A by 100 into density. So that density would have been 1.025, because the hydrostatic tables are made only for salt water. So I'm going to fill up that, and that is what I have written in a slightly different format. My aim is to find this constant. Why? Because 100 is not going to change. And that water plane area at 5-meter draft, doesn't matter whether you're floating in seawater or freshwater, is going to be exactly the same. So I'm going to find this constant called A by 100. So A by 100 in this case will be 25 divided by 1.025. How I got this? I just reshuffled this violet color equation. I just reshuffled, I just put it here. I put 25 A by 100 into 1.025. The moment I get one A by 100, I can calculate the TPC of dock water. So all I'm going to do is use A by 100 in the same formula which is in the violet color, but this time I'm going to put the density of the water in which I'm floating. So what I did was 25 divided by 1.025. This is the value at that particular 5-meter draft, and I multiplied, I got an answer. Let us say similarly, I'm floating at same 5-meter draft in freshwater. You can see I've done the same thing. A by 100 is 25 divided by 1.025 into 1. So this is the way you can interchange between any densities as far as your water plane area is known. And when you are in the same draft in different densities, it is very evident that water plane area is not going to change. It is just exactly the same. Let us go to the last definition for today, which is called reserve buoyancy. Let us quickly look at it. It's very easy when I put you with pictures. Let us say that a vessel floats right now, it's at its permissible draft in waterline. Let us say you are in summer zone and summer load line. So I'm just showing you right here with a red color mark as my summer load line. So right now, this is the condition. So a few things you need to understand. This is partially immersed. This is your draft. At the same time, that directly governs the underwater volume. What is on top is your freeboard. At the same time, I can call it above water volume. Okay. Now I ask you a question. At this condition, right now, this is my, let us say, sailing condition. I will ask you a question. How much more can you immerse this vessel to a maximum without sinking it? So going by the flotation principle, this is the condition. So I'm fully immersed. That means now after this, I don't have any more volume to displace. So hence there's a high risk of sinking. Why? Because after this you add weight, then it goes beyond the displacement of the water which this body can push out. So that means this is the simple way of understanding what is reserve buoyancy. So basically, what is the volume you sunk extra to reach the right-hand side picture is what is called your above water volume. That is the extra you did. You are supposed to be like this. I have some extra which is called above water volume. In other words, your above water volume right now, what you have in this condition is what is called reserve buoyancy. So the reserve buoyancy is the extra volume you can displace maximum without sinking the vessel, or in other simple words, I can call it volume of enclosed space above the waterline. That is the simplest way of understanding this. It is given in a particular format. Let me just show you. Reserve buoyancy is equal to total volume of the ship, complete volume, minus the underwater volume. And that is what is your above water volume. Okay. In other words, I can put it as a percentage also. So normally you will see that many of the questions will ask you an answer in a percentage. How should I give a percentage? Is nothing but your above water volume divided by the total volume of the ship, and you just multiply by 100, and that gives you your RB in percentage. So this is how reserve buoyancy is expressed normally. This is the way it is expressed. Okay. So that was the last definition for today. I hope this was useful, and I'll catch you soon with the next series. I might go one more session or definitions. So till then, please keep watching Jal Prayag, and Vanakkam, Namaste.